Welcome everybody to the design and simulation of a centrifugal pump by Group 3. The members of the group are Angel Rodriguez, Hassan Vergara, and myself, Tomas Bravo. Now, before we start, let's talk about the table of contents. We're going to talk about introduction, literature review, materials and methods, results, discussion, and conclusions. For the contextualization, we have that centrifugal pumps are highly used in multiple industries such as food, pharmaceutical, petroleum, etc., because of its easy adaptation. And in the concept itself of CFD, it can be defined like resolving flow problems using numeric solutions and algorithm.
Regarding of the state of the art, a bibliographic review of different articles was carried out, which allowed deepening the knowledge about the operation and the dependence of the performance of the pumps based on their design parameters. Among this bibliographic review, the article Design Techniques to Improve the Performance of a Centrifugal Pump by CFD was analyzed, which contributed to the field of understanding the characterization of the performance of a centrifugal pump from the parameters and initial condition of operation using CFD as a tool. Additionally, the article CFD for centrifugal pumps was reviewed, a review of the state of art, which allowed us to understand the scope that explained cavitation and axial flow as the main challenges in pump design, its causes, and the impact it generates in the operation of a pump on an industrial scale, taking into account the damage caused by these variables in the industry. Finally, the article CFD Design and Analysis of a Centrifugal Pump was reviewed in order to understand the effectiveness of CFD in the study of performance of a pump by analyzing the pattern in the speed, profile, and pressure distribution that the pump presents by modeling it digitally.
Now for the objectives, we have that the main goal of the project was to design and simulate a centrifugal pump following Goldich algorithm. On the secondary goals, we had the use of Autodesk Inventor, Excel, and Star CCM Plus to do simulations and design of the pump. For materials and methods, we can divide the project on 4 stages. The first stage was to design the pump on Excel. Here we established the operation conditions for the pump, such as flow rate, mass flow, viscosity, density, temperature, angles, number of blades, and numeric design of the volute and impeller. Then on stage 2, we make the creation of a 3D CAD model where we import the data from stage 1 into the app Inventor Disk 2021 and design the volute and the impeller. Then on stage 3, we did the meshing where we import onto Star CCM Plus the models of stage number 2 and we could implement the conditions defined in stage number 1. And finally, in stage 4, we did a simulation for multiple flow rates for water and mineral oil. Now, in stage 1, we designed the pump on Excel by plotting points of flow and total head and finding efficiency best point and optimum variables. The initial conditions can be shown in the chart below, where you can see angular velocity, optimum flow, entry angle, outlet angle, gravity density, and viscosity, also for water and for mineral oil. We can find also the equations for the hydraulic power, the plot of the volute we designed with 8 plates on Excel, and some initial conditions for suction pipe and discharge pipe. On stage 2, we developed the impeller and volute on Inventor by importing the data and extruding it. Here we can see the 3D models of the parts and the assembly. You can see the impeller, the volute, and an assembly of both parts. On stage 3, we did the meshing where we started with a million cells mesh with these conditions. Base size 2 centimeters, target surface size 100%, and optimization cycles 3. We also had a manufacturer data to compare with. That was the total head 120 and efficiency 73.8. We run this mesh of 2 centimeters base size and we obtained the following results when we had a total head of 124 meters and efficiency of 70.14%. For the thin layer, we were supposed to decrease the base size on 30%, but this caused problems of recirculation in the inside of the impeller and the cut water region specifically, which would later cause negative and wrong data for the reports of brake power and efficiency. So we only changed the target surface size to 80% and we run this layer. We obtained the following results. Regardless of this, we decided not to use the thin layer because of its high compute time and the differences with the manufacturer data. For the thick layer, we increased the base size to 2.6 centimeters and obtained the following results, where we can see a total head of 125 meters and efficiency of 70.77%. Here we can compare it with the manufacturer pump data. This mesh was selected as the best mesh because of its closeness to the manufacturer data, and it was used to make all the simulations from now on. Finally, on stage 4, we simulate a total of 15 simulations, 9 for water and 6 for mineral oil. pause the simulations, we change the flow rate and run 5 main simulations first that were shut off, midpoint, manufacturer's BEP, Freely, and our BEP that we can see how we find it in the next screen. Here we can see how we find our BEP calculation. We did plots of flow rate versus efficiency and flow rate versus total head, and we obtained the equations of the curves, and then we obtained the best BEP or the best efficiency point from these curves. In the final part of methodology, we plot cells against water head MSE, that is the error of total head, and against total solver CPU time, and a plot of cells against efficiency error and total solver CPU time. Here we can observe and analyze the behavior of how, if we decrease the cells from the thin layer to the thick layer, how this changes the variables of error in the total head and error in the efficiency.
Speaking about the results obtained in the impeller velocity profile, it can be seen that it's the same profile for both fluids regardless of the flow rate, since its rotational speed remains constant throughout the simulations. This is why the same scale of values is presented for both fluids. However, speaking about the worldwide plus, it is evident how the design of the pump allowed to obtain in this parameter less than 5 during the entire passage of the fluid through the pump, since there is no significant difference in the results at different flow rates. This means that the applied mesh was accurate enough to determine the behavior of the fluid near the wall, that means in the viscous sublayer. However, it can be observed in the scales how the worldwide plus of the oil oscillated between values much lower than the values of water, which means that the behavior of the oil in the viscous sublayer is better determined by the mesh because this is a more viscous fluid. On the other hand, when analyzing the vector and scalar velocity profile of the pump, it can be seen how there is a higher velocity in the impeller than in the rest of the pump, and you can see how the greater the flow, the greater the speed. Additionally, a recirculation behavior is observed in the inner side of the volute, due to the fact that the cut water is not acting as a dividing wall that separates the fluid so that it exits through the outlet. Rather, that it is acting as a hole that allows the fluid to re-enter to the impeller, increasing the speed at this point. This behavior is also observed in the streamlines, where it is seen that the fluid re-enters to the impeller instead of exiting through the outlet. Observed in the streamlines, where it is seen that the fluid. The information above means that the pump is poorly designed. This is confirmed by talking about cavitation, because this is observed that there are points near the center of the impeller that cavitate. Those are the internal parts of the plate. Taking into account that at these points the absolute pressure is less than the vapor pressure of the fluid, creating a negative suction that tends to damage the pump, because cavitation allows the fluid to boil and create bubbles that affect negatively the pump. This cavitation is minimal. However, since it is present, it reduces the efficiency and effectiveness of the pump. Ideally, the pump should not cavitate, indicating a good design. Again, the poor design of the pump is confirmed by analyzing the head graph obtained from the flow of water, because it is understood that the unusual behavior that it presents is caused by the presence of an actual flow, which means that there are two or more points of flow that have the same head. This flow affects the efficiency of the pumps and therefore the location of the best efficiency point.
Alright, I'm going to present the operating curves. As shown in the figure, the total head versus the flow rate of the manufacturer pump and the design pump with water and oil. As mentioned before, we present actual behavior in the flows of water and oil, in comparison with the manufacturer's curve that has a radial flow, which is one of the target flows when we design a pump, since it provides optimal behavior in a certain range. On the other hand, having an axial flow, it was necessary to calculate and simulate more points at different flows. This with the objective to find the operating range of the pump, because in this range the behavior of the flow will approximate in a radial flow. In addition, the aleatory errors were caused by the assumption made to find the working range, which propagate the error. Well, so when the operating range was located, we find the best efficiency point when the pump works with water and oil. First, the efficiency of water is 79%. It was obtained at a flow of 252 cubic meter per hour. Finally, the efficiency of mineral oil is 66%. It was obtained at a flow of 217 cubic meter per hour. The figure shows that the manufactured BEP was found in a shorter flow in contrast with the BEP of water and oil. In conclusion, If we want to use the pump that we designed with fluids like mineral oil or water, we have to operate the pump in flows greater than 162 cubic meters per hour. The pump has a recirculation problem due to the size of cool water is big. As a result, the pump presents axial flow in flows lower than 160 cubic meters per hour. Finally, the BEP efficiency of the pump in the operating range is greater than the BEP efficiency of the manufacturer pump.